Hi, today we're going to talk about atomic mass actually probably falls right out of yesterday's lesson, come to think of it. As a bit of a do now, here are three questions for you to answer. Speaking of yesterday's lesson, there's a reference table above my head, so make sure that you're using it if you need it. But otherwise, I'm going to get started. Notice that for the magnesium symbol, you're not going to find a number in the bottom left-hand corner. You might not always get one, but you can go fill that in with your periodic table really quickly. That's a 12, and that helps to figure out this. It's an ion with a charge of 3 plus, not plus 3. Slight difference, it doesn't really matter. Neutrons would be the difference between the 25 and the 12, so 13 neutrons. How many electrons found in an atom of silicon 29? Well, atom means neutral. Silicon is atomic number 14, so the answer is 14. 7 protons, 6 neutrons, 10 electrons, charge of 3 minus. There's that minus again. So for today, I wanted to talk a bit about that word that I kind of mentioned in the previous lesson, but didn't really expand upon. The atomic mass is shown on the periodic table. This is not a mass number. So we have atomic mass, mass number, and atomic number, and they all mean different things. Wonderful. But this atomic mass is frequently a decimal, right? You can see it's 12.011. And then I actually went and found the main isotopes of carbon from Wikipedia. I know what you're thinking. Wikipedia is not a bad source if you're actually checking your references and if you're using it for like an encyclopedia. There are 4 listed here. None of them are 12.011. And there's only 1 listed on the periodic table. So the real question I have with this is, how is it that you get from those 4 to this 1? And so to talk about that, I figured we'd mention candy. I like Snickers. It's October. I'm thinking of Halloween. One of the things you might think is with 4 isotopes of carbon that you would want to average them. But similar to these Snickers, if each of the particles is slightly different, a straight average might not get the point across. We had carbon 11, 12, 13, and 14 on the previous slide. However, the number that you see on the periodic table is not the average of 11, 12, 13, and 14. That's 12 and a half, and it says 12.011. And similarly here, we wouldn't want to just take the average of 9 and 52 because that doesn't account for the fact that there are, in this sample of Snickers, 3 minis for every regular. Really, though, if you want to take the average, it's easy enough. You just add 9 plus 9 plus 9 plus 52.7 and divide by 4. And what you end up getting when you do that math is 19.925 grams, which is a lot closer to 52 than just taking the average of 52 and 9, which would be about 30. Actually, no, I said that backwards. It's closer to 9 because there's more of the smaller pieces. But then if we're going to round this for significant digits, we added and we had a whole number there, which would add up. So we probably get 2 significant digits. So we're going to go to, say, 20 grams as our average. So again, just to clarify what I said before, if you just took the average of 52 and 9, you get something in the 30s maybe, or high 20s. But since there are more minis, the average should be closer to 9 than it is to 52.7. And that kind of makes sense, right, when you've got 3 objects like that. However, when things get a little bit more complex and you have a different assortment of Snickers bars, even got some Snickers with peanut butter in there, it makes a little bit less sense to say 9 plus 9 plus 9 plus 17 and doing all that. You might want to do something that makes your shorthand, your writing a little bit easier. You can say 3 times 9 plus 6 times 17 plus 2 times 50.5 plus 52.7. And then when we count them up, you end up with 12 bars, right? So if you grab your calculator and you do all that math, you get 23.56 grams as an average weight, which would then round to, I think we're going to do the whole numbers. So there'll be 2 significant digits, so 24 grams is the average Snickers bar in this set. Which, again, if you do all the math and you just add up 9, 17, 50.5, and 52.7, you get 32.3. So that 32.3 is not a good estimation of the average bar because of the relative numbers. Now, what's nice about this setup here, I'm going to change colors to make my point, is that this setup's actually kind of well suited for pulling apart our formula and writing the formula in a slightly different way. If we factored out the twelfths and what, we could factor out some of the numbers on top, you get a setup that kind of looks like this. You get the same exact answer after doing this, but what is nice about this setup on the bottom, I just factor out the 12th and then the numbers up top, is that these numbers, these 3/12ths and 6/12ths, they represent the makeup of the Snickers bars as a whole. A quarter, 3/12ths of the Snickers bars are the minis. Half of them are the fun size. And so we're kind of working in this percentage, this composition term to our calculation, and that's actually how we approach doing a weighted average for the atomic mass found in the periodic table. So going back to our formula, or data here from Wikipedia, this carbon-11 is synthetic in abundance, so we're not going to count it. And the carbon-14 is 1 part per trillion, so it's way too small to actually impact our math at this level of significant figures. But we're going to do the same thing as before, where we talk about the percentage or the fractional composition and multiplying it by the mass to get our weighted average. It's percent times fraction times mass. So we have percents over here. We can't just write, we could write that as a fraction if we wanted to, but I think I'd rather write it as a decimal. So for atomic mass, we're just going to multiply the fraction, and I say fraction, but that can mean also the decimal, like if you're talking about like percentages, times the mass for the first substance or first isotope, and then the second, the third, the fourth. So we're going to write this out really quick for carbon here. And when you grab your calculator and do this math, you get a mass of 12.011. Hypothetically, we'd be rounding this, but I think all of these reference values already on Wikipedia are slightly rounded. I like a lot of their information, but sometimes it's not fully internally significant figure consistent. There we go. But we do see that this is the number that we get on our reference table. It's also on this table here. So that's how we calculate atomic mass in terms of elements on the periodic table. You need to know that percentage. However, if you have your periodic table, you can also, knowing that that is what that number means, you can use the periodic table to inform a little bit about the elements, even if you've never seen the data. So looking at these numbers here, I'm going to start with helium. I think when the weighted average is 4.002, that means that whatever isotopes of helium exist, and I don't know off the top of my head, it means that probably that number that's in front of that 4 is very, very close to 100%. It's probably 0.99 something. And then when you add the other ones, there's going to be a very small decimal. See, what you can see in the math here is that when the percentage is high, this number is very close to 1, and these numbers are very far away from 1. They're almost 0. And that's why you end up seeing that the weighted average of 12.011 is closest to 12, which is the most common isotope. So here you can say the same thing. The weighted average number, the answer, is closest to the most common isotope of the element. So the most common isotope here is probably helium-4, and the most common isotope for chlorine is probably chlorine-35. Is that a guarantee? No, not really, but it is a good, quick estimation that you can make moving forward if you don't have any other information. And then if you wanted to get an idea of what other isotopes might exist, you can look at where this number is in terms of the decimal. I mean to say for chlorine, 35.45. Well, if the most common isotope is 35, the only way the weighted average is going to be greater than 35 is if a heavier isotope exists. And it does turn out that the other main isotope for chlorine is 37. And then for helium, we can then assume that there's going to be a helium-5, maybe a helium-6. They'll be small in abundance, but they will be non-zero. Again, not a firm rule, but it's a good estimation you can make. So in summary, there's your definition for atomic mass. The numbers actually do change over time as we take more samples. You might assume that we haven't measured all of the helium atoms in the universe or all of the carbon atoms in the universe. So the number actually does change over time, which is kind of neat. There's your formula to plug in. The one thing I will say is make sure your abundance is written as a decimal. And if your abundance is less than 10%, that you insert that extra 0, right? 1.1% is 0.011. Thanks for watching.